So welcome to my introduction about the new ARM architecture, the new ARM v8 64-bit ARM architecture. My name is Thomas Ross. I do embedded security and mobile security, mostly in the direction of bootloaders and so on. And yeah, we're going to take a relatively short look at what's new in the architecture and what changed and how does it make my job different and how does it change the future of mobile exploitation, for example, for jailbreaks, for hypervisor evasion, and so on. So this is the basic roadmap of the history of the ARM architecture. It started with the relatively old ARM v5, ARM v6 instruction set, and then on current mobile phones, you are most likely using an ARM v7 based processor. With ARM v8, ARM v8 is basically the biggest upgrade to the instruction set since it was invented. In ARM v8, we have stuff like mandatory floating point. We have a 4-tier exception level based architecture of hypervisors and so on. And if we look at most changes in ARM 64-bit, it's really focused on high performance applications. So while the normal 32-bit ARM is very good for small devices, for minimum power consumption devices, with ARM 64 we can actually really do massive processing. A lot of the instructions contain stuff like hints for pipeline optimization, for caching optimization, and so on. We don't have the old CPU modes anymore. We now have so-called exception levels. We have virtualization built in, and yeah, the instructions are still 32-bit fixed length though, so you're not doubling your code size. We have much more registers. We have a divide instruction finally. If you've ever written embedded ARM code, you will know what a pain it was to actually divide something in your bootloader. We have a compare and jump instruction instead of conditionals on each and every instruction, and we can still also run 32-bit ARM code. So if we compare it to the old instruction set, there are some main difference. For example, there's no more thumb mode. Thumb mode was an instruction set on ARM that basically was the normal instruction set shrink down to 16-bit instruction. It was very limited, but very small, and also very good for compilers to generate because it was so simple. Another thing that's missing now are conditionally executing instructions on ARM 32-bit. Each instruction could have a condition in it. So you could, for example, have a block, instead of having branches for comparison and so on for ifs and else, you could just have a 4-bit in the instruction set differently, and it would compare it per instruction. We also don't have a coprocessor anymore, which is the thing that you used on old CPUs for your MMU configuration, for your entire power management setup, for your caching, and so on. The program counter is not writable anymore, only by branching instructions, but we have almost double the registers. If you want to get started with a bit of ARM 64 development, there are some official ARM simulators. There's the iPhone 5S, if you can get your code to execute on it. There's the Versatile Express, which is basically an FPGA-based implementation of the ARM 64, and there are some other boards. And also very cool is that QEMU now has full support for, actually since quite a long time, full support for AARCH64. If you want to analyze binaries or generate binaries and want to reverse engineer existing ARM64 code, most tools are already up to it. In IDA Pro 6, some months ago, there was an update that now supports ARM64-bit GCC can generate and object dump, can disassemble the the code. The Hopper disassembler, which is a very, very nice and cheap alternative to IDA Pro, has limited but working AARCH64 support. And if you want to debug something or want to test your shellcode, you can just run it in QEMU and are up in no time. Alrighty, so let's talk about the architecture. If you've ever worked with normal ARM processors, you will know that you had like 16 registers, some of which were banked between the different interrupt levels and so on. And now you actually have 30 general purpose registers and also a 31st register, which is either the stack pointer or a 0 register, depending on your context. For the first 8 registers, which are unintuitively at the bottom of this slide, are for parameters and results in your function sets and are never banked between calls. The 8th is if you return a pointer, and then you have some 6 scratch registers, some interprocedure call registers, and so on. It's actually quite easy. The one that, if you write exploits, you'll be confronted with the most will be register 30 and 29, which is the frame pointer and the link register. Yeah, basically everything like before. A cool thing is that all registers can be used either in 64-bit mode or in 32-bit mode. So if you, for example, you have an integer implementation where you work with 32-bit integers, it won't be slowed down by checks where, for example, if you rotate shift something, you have to copy over the first half into the second because you need 32-bit shifting. The instruction set has that all built in, and you also have 32 additional floating point registers, which is useful if you're into science stuff. So on the old ARM CPUs, we had the different modes. Basically, if your applications were always running in user mode, your operating system was running in the system mode, and then some parts of your system might even run in the supervisor mode, which is a slightly enhanced system mode, and so on. It was very, very difficult to build it for virtualization and so on, because if you only have one fast interrupt handler, and it's a dedicated CPU mode and so on, it was a lot of overhead if you actually did real virtualization, because an interrupt was firing, you had to check what VM am I in and what am I actually supposed to do, and you couldn't have a real hypervisor or monitor mode underneath your guest operating systems without a lot of overhead. They get rid of that, and now we only have 4 modes left. We have the, whoops, sorry. We have the EL0, exception level 0, which is the unprivileged mode where your applications run in. We have the exception level 1 where your operating system, your kernel, and so on runs in. Then we have a third exception level where your hypervisor, for example, on your desktop it would be your VMware or whatever runs in. And then underneath that we have another mode which is called the secure monitor, which manages the state switch between the normal mode and the so-called secure state. This graphic shows a bit how it could look on actual system. You have your applications in exception level 0. Basically, the lower the exception level number is, the lower are your privileges. And for a normal server system, for example, it could look like this, that you have a hypervisor, which is VMware or whatever, or KVM, and then you have your guest, which would be Linux, and then on top of that, your applications, and then also monitor mode, and the monitor mode can be called to switch into a secure state of the CPU. In the secure state, exception level 2 is missing, but you can run a secure operating system which can provide functions to your guest, to your hypervisor, for example, for cryptography. So even if your hypervisor is owned, your secure area won't be owned because it's entirely dedicated and separated by this monitor layer, which is quite cool and quite similar to what we do today with TrustZone. And I'm quite excited to see the first evasions from app to the bottom and up again on the right-hand side. All right. Each privilege level, except exception level 0, can set what causes a level change. Basically, you could have a hardware button that causes the CPU to jump into exception level 3, or you could have, as soon as a specific data access happen, your CPU can jump to exception level 2 to your hypervisor, for example, to manage direct memory access with hardware or whatever, and so on. Alternatively, you can also explicitly call down from your exception level, just never up. So exception level 0 could just issue an SMC instruction and it would jump into the CPU monitor depending on your exact configuration. It's quite cool because you can very finely configure what happens with the different permissions of the exception level. So you can, even your operating system level can be very locked down and very limited in what it can do, which could be interesting for if your hypervisor is like a microkernel or something. Yeah, there are also 3 different interrupt vectors for the exception level. So each exception level has its own interrupt vector, can handle its own interrupts, and so on. And for example, an interrupt that happens while the CPU is in exception level 0 could go into the exception level 2, but then the exception level determines, okay, I check this interrupt, I can give it up to the operating system again because it's nothing they need to care about. I mentioned it earlier, the coprocessor, which is used to configure your MMU, your caching, and so on, is all now gone. It's basically not this architecture where you had a separate coprocessor in your head. It's now all done via dedicated or system management instructions, which, yeah, it's quite a nice change, and it's still backwards compatible. So you can even, if we go to the slide, you can even have guests that still run in ARM 32-bit, but the hypervisor is ARM 64-bit, and the second guest is ARM 64-bit too. So it's really cool because you can just from the bottom up change your architecture however you like. So you could even go and run 64-bit ARM Linux or in 32-bit ARM Linux, and the old register banking that happened before is now mapped onto the new registers. Alrighty, for the 3 privilege levels, we obviously need to have different memory translations because each your operating system must not run in the same address space as your second operating system. And so in the worst case, you have a 3-stage translation of your memory addresses from virtual to physical, which seems to be fast enough, and it's quite cool because you can shift your whole translation tables around, and each operating system still, without any penalty, can manage its own memory. No need to call your hypervisor for doing all that stuff. Yeah, the function prolog and epilog on ARM 64 is a bit different to what happened before, because before on ARM 32, you basically, when you went into a function, all the registers you were going to touch, you just banked them onto the stack via store multiple register instruction. Unfortunately, or why ever, this instruction doesn't exist anymore. Now you can only store and load pairs of registers. So the compilers, even right now, compilers already optimize a lot in that direction. So they try to avoid using a lot of registers, even though they have a lot of them available, because you would have to have a lot of store pair instructions to store 30 registers. But yeah, the basic prolog just stores your link register and your frame pointer onto the stack, configures the stack with the -32 to reserve the space for your local function variables and so on. And the epilog does the same, just backwards. It loads your link register again, it loads your frame pointer again, adds 32 byte to the stack, and returns. The return instruction does nothing like on x86, where it pops, addresses, and so on. Return really just sets the program counter to the current content of the link register. So it's just an unconditional branch. It doesn't do any magic like on x86. So if we look at some example code of a very, very simple ARM64 function, which just takes an integer, calls another function, and adds to the result of that function, this would be what the current GCC without optimization would do. So it stores the current link register and frame pointer. It moves the current stack pointer into the frame pointer. It stores the argument that was supplied to the function into onto the stack. The 16 is basically the offset to the frame pointer, and then it goes and calls foo. The reason we copy the argument over is that we can't be sure that foo won't touch register 0, because register 0 is always used for return values. So foo returns, we copy the return value into a register. We load our argument again. In this case, the compiler optimizes a bit shitty. We add them together and then just restore our frame pointer, our link register, and return. It's that easy. It's really a breeze to read because the amount of instructions you have to know is really low, and it's very, very comfortable to write and read ARM64 code. Alrighty. Now, as a very small demo of how you can run ARM64 stuff on your computer. Great. So I have a monitor down here. That's basically we can just use the current QEMU JIT has full AARCH64 support, at least enough to boot a Linux on it. And if you want to experiment with real ARM64 userland, you can even just get the Linaro builds and run them in QEMU. So for example, in this case, all this stuff will be on my GitHub after this talk, and if the internet in the hotel works today. In this case, we can just boot up a Linux kernel in ARM64 mode. And if the scrolling works, that would be great. Wow. Yeah, and now we can log in. This is the build route that's normally used by to compile stuff for the architecture. And as you can see, we now have a test userland that runs in ARM64, and it's really easy to use. To look a bit at the reverse engineering workflow, I've also prepared a small demo of the Hopper disassembler. For example, this is a bit too big, I think. So in this case, this is part of the code we had before, just in this case, a whole executable. And I can now just take the Hopper disassembler and load my binary in there, and it will immediately the screen is a bit small. Will immediately find all the symbols if included in the code, and I can just navigate the code and see that the code we had earlier is pretty much exactly what Hopper tells us it is now too. So it's really, really a breeze to navigate with the tools we already have. A lot of them will come, I'm sure. I also have some IDA Pro scripts which you can find on my GitHub, which allow you to basically automatically search for ARM code, ARM64 code in the blob. So for example, if you have a bootloader and you load it into your IDA Pro, you can run the script and it will look for the function epilogues and function prologues automatically to see functions in binary blobs where you have no idea if they are actually code or data and so on, and it tries to sort it a bit. All right, so for exploits on ARCH64, unfortunately, we can't go in depth because of our time limitation, but I just want to give a very short overview on how it's a bit different from ARM32 in regard to the stack offsets and so on. But overall, it's ARM64 has the standard mitigation technique, so you don't just have an executable stack and heap on your operating systems. Return to libc is not possible because at least the first 8 arguments will be in registers and not on the stack. And yeah, unfortunately, compared to ARM32, especially when you're working with bootloaders, we often have very small functions. It's difficult to find good gadgets to configure registers as you want. It's an important goal if you want to be able to call random functions and not just return-oriented programming gadgets, to have a function which loads memory into registers, because the load multiple instruction is now missing. Most compilers don't generate nice gadgets for us anymore. So yeah, as I already said, return-oriented programming is the way to go, as always at the moment. And yeah, if we compare the epilogue of an ARM32-bit executable and an ARM64 executable function, we see that in ARM32, the program counter, the instruction pointer in the memory where the current code is executed, was directly loaded from the stack. This is not possible anymore because on the new 64-bit architecture, the PC, the program counter is not writable anymore, and it can only be modified by instructions like branch instructions and return instructions. This is mostly, as I've been told by an ARM engineer, because of pipeline stuff. Basically, the pipeline needs to be flushed on a return instruction and so on, and even the return instruction signals to the CPU that this is not just an unconditional branch. You can do other optimizations because this is a return and so on. It's quite fascinating. But yeah, it's just important to know that basically we load the link address and the previous frame pointer from the stack, and the return will jump onto the stack. So this is very, very strongly simplified version of code from a specific bootloader which already runs on ARM64, and it basically gives you, oops, I have the wrong code. It basically gave you the chance to supply a recovery script that's booted on the first boot, but you had to have some authentication to actually run the do command function and so on. But I was able to find a stack overflow in the bootloader itself, which could be used by a USB protocol message where you can just have full control over the stack. And after a while, I found this reverse engineered stuff in the bootloader, which basically allows me to execute whatever I want on the system, given that I can control the recover shell script, which I actually can. So return-oriented programming basically means that we want to return from one function to another, and we control where we return to. So in this case, we get, by overwriting the on-stack link register, we get our code to jump to the return statement here to temp recover.sh, which will return the address of the string into register 0. And then we want to jump to the system call, because then we can immediately execute the shell script listed above, because nicely the get recovery script function configured register 0 very nicely for us with a path that we can even execute. So yeah, we want to jump to the address set of the first instruction. So then we want to return via the stack, via the frame that's stored on the stack to the system, and we have a root shell in this case. It was a very easy case, and it's on quite an interesting device, but I can't get into more details yet as we are in responsible disclosure. Yeah. So basically, what we do, like on most devices, on most modern exploits, we have a Stack Overflow. Above this, we overwrite the link register. We write our own frame pointer, and after that, we put a second link register and frame pointer onto the stack. So under Stack Overflow is basically the downwards growing stack, and we just configured our link register to point to the return statement of the get recovery script, and our frame pointer, which will be loaded by the return as the new link register and the new frame pointer address. Our frame pointer points to a Stack Overflow controlled link register. So the return, instead of returning to wherever we came from, will actually return to the system statement and give us the possibility to execute whatever we want. And that's basically it, just a basic overview over the AARCH64 instruction and set. I hope you have fun, and thank you. Cheers. Are there any questions on the topic, or just bug me later here? All right, thank you.